stock answer. How short you remember.
Professor Ewing?
Yes, sir.
Do you know if the Control Z to go back one step function works in Microsoft Access?
I didn't know Control C took you back one function.
Like in Microsoft Word, if you delete a paragraph and you didn't want it, you hit Control Z and it'll make it appear and take you back basically a step. But
It's a redo. I didn't know that.
oh, okay.
I wish I did know that.
You can hit Control Z until you're all the way back to a blank page.
Control Z or C like Charlie?
Z.
Like zebra.
It'll go back, yeah, like 30 steps, I think.
Useful.
I was just thinking because Access is so convoluted that like sometimes just wanting to get out of there, just get me out. Control Z, 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 Z.
Just go in there and do a new one and make a mistake and try and do it.
Yeah, I don't have Access, so
Oh.
yeah, I'll have to mess with that tomorrow.
I left you a candy.
Thank you. What's this thing?
So 3 minutes and we're up and running. Hi, Jeff.
Hello.
I didn't do it. So, can everybody else remember me help when we put the access up there? Try to turn off the room lights because it's not showing on the video. I see that the cup says Java on it.
This is black coffee.
Yeah. Java is sort of a word for coffee.
Got it.
Java is also a programming language, which we'll talk about later today. So does anyone know the story why Java is called Java?
Does it have anything to do with the island of Java?
No, it has a lot to do with an oak tree. It was developed as Sun Microsystems, since acquired by Oracle. Larry Ellis, the man's name I'm trying to remember, started Oracle. And the man who was in charge of the release of this new programming language at Sun, he decided to call it Oak. But he got overruled not to call it Oak, kicked back to him. Marketing says no one's going to talk about that. He didn't know what to do. And a clock was ticking. Saw a cup of coffee on his desk. He says, "That's it." That's how it happened. Genius. And another great programming language is the C language. This is an easier story, also true. So why is the C language called C? Because it comes after B. So the person who created it at the Bell Labs, he'd been messing around with the earlier language called B. He just named it B because he didn't want to pause to give it a real name, and it wasn't working, so he started a new one which he called C.
And it worked.
Very well. Very, very well. Dennis Ritchie. Worked very, very well. Fabulous one. Okay, so we're ready to begin. And the first item of business, I'll pass you out a cartoon, which is on everybody's mind since your recent experience of 2 classes ago. No, the other side, show for the cartoon. Yeah. Read the cartoon, please. Now, how many of you say, well, that's something that you've been doing for a long time now? Nothing new there. Okay, so let's go to the back side of this and look at why it's really, really hard to fail this course. It's never been done. Could be you. Somebody's got to be first. Feel challenged. These are the grade windows. So if you get 100 on the attitude, and many of you do have an attitude, attendance, punctuality, and homework, and you get 100 on your projects, you can get a grade of A in this course with an 83.3 average on the test. Get a B in this course with a 66.6 average on the test. And you get a C in this course at only 50%. And if you're really determined to fail this course, you've got to go below 33. So with that being said, I'm going to return your test ones to you. Now, when I return these to you, on those fill-in-the-blank questions, you're going to find maybe up to 4 of them that you disagree with my grading, that you think there's an argument for your answer. I'm going to make that argument very quick. You just won. So I increased everybody's grade by 2 points, which is equivalent to 4 argumentative questions. For example, if I'm looking for a disk that's too spread out all over the place, some of you say scattered. Some of you say shuffled. But that's what you do before you take this course. After you take this course, you call it what is properly called, which is a fragmented disk. Hi. So shuffle along.
So let's just circle it. You guys do.
Yeah, but take your time on it. So, analysis, we've got 4 people sitting on an A, 4 people sitting on a B, 2 of them very high Bs, could slip into an A easily, and a solid C here. So that's where we sit after the first test. So, overlook them. It's always good when somebody gets a good score, because that shows you that the reason you didn't get a good score was you. Just double check that. As I looked at the trial tests that you used to prepare with, some people hadn't done them, so that's also your choice. Now, this is only one test of 4. So if you got a good score, there's still time to mess it up. If you didn't get a good score, there's still time to get where you want to go.
I have a correction.
Okay, see me privately, we don't want to bore 8 other people. In other words, I failed to find a wrong answer, right? Yeah, that happens sometimes. So, in the 412 years I've been teaching, we have a large number of people that came up for test corrections. 3,422 of them said that I failed to give them enough points. How many came up said I gave them too many points? I did get 3. Gave them too many points. I couldn't stand it. So it'll take another few moments to examine this. Some of your blank answers were highly original, and you obviously had no idea what the answer was.
That's definitely.
You pulled something out that was fun to read. I'll say that, it's definitely fun to read. But almost everyone lost the points they lost on the fill in the blank questions. Which had to do with how much research you were willing to do to find those answers. You had good 4 days notice, and so if you just wanted to wing it, then you didn't use the 4 days. So test 2 will be coming along and the same format. Give it to you 2 classes early.
Do you want the score circled with our initials or whatever?
Just circle the score and I'll pick it up when you've had enough of looking at it. Blades was the,
Number 1 missed.
it was right in there, Blades. Certain people recall their failures, other people recall their successes, so depending on which type you are, you might recall Blades or something. Yeah, circle it grade, it doesn't mean you agree with it, just means you saw it.
I'll take the bigger grade.
It's a deal, it's a good deal. Avoids a lot of discussion. Okay.
Somebody really do it. 95?
Yeah. Person with a 95 had a totally completed trial test. Checked and double checked all the answers. Yeah, got the 95, so. Zuza, I got your test. I'll take it now, you can look some more later. Okay, so, it's hard for me to find material that's testable. It's easy to find material that's detestable, but I try to avoid that. So are there any comments, questions, remarks about where we're at, where we're going? Course is in good shape. And don't cry, but this is our last Friday. Okay, we're back to a sane schedule. Workshop tomorrow from 2 to 4. Come in, do what you want in the room, space is available. And I do encourage you to hit the YouTube and find movies on these topics, little video clips, another resource that you can use. And, yes sir?
Yes, tomorrow, I know that you're doing a lot of math and statistics stuff, but if I did have a question about access and I bring my project, is there a question I could ask you here, or is that
Well,
something that's?
no, that's what I mean when I'm inviting you.
Yeah,
You're invited to this workshop on equal status with any member of any other class that comes.
okay.
So, yeah, you get attention, don't worry about it. 2 to 4 tomorrow, this room. God, divorce, philosophy, all topics are all on the table. Now, today's material was chapter 13. So let me quiz you. Jeff, what do we mean by a procedural programming language? A procedural programming language.
Programming language that is run by procedures. Perfect.
You guys been having coffee together or something? Mike, can you
That's
improve
how
on
we're
that?
supposed to answer them here. That's how everyone else said.
That's what we
do. I agree with it.
You wanted to improve on that, any?
Yes, I can.
Yes,
Procedural programming is
Yeah.
done by step-by-step instructions.
that's much better. That's much better.
I meant that when I said procedure.
Okay. Now, in a procedural programming language, the data and the data handling process is distinct from the code that operates on the data. And when that was integrated into one type of programming language, it was no longer called a procedural programming language. It isn't called a what, Jordan? What was this? What was the next improvement on this type of languages? The initials are OOP.
Object oriented.
Object oriented. Now, in an object oriented programming language, the description of the data is in the same object as the code that operates on that data. And they move around as one object, such as in a company, you could have an object like an employee. And the data on that employee, such as his ID, address, performance record, is integrated into one object with the code that operates on that, such as calculating his salary or any other such action that would be taken against the employee. They're integrated into one object called an object. The advantage of this is objects are transferable from one program to another. If you're going to write an accounting program that involves this employee, you don't have to start from scratch. Just plug the object into your program. The code and the data descriptions are already done. So things just have to be done once and used in many, many different places. So the next improvement on that was called an aspect-orientated program, and in which case you take an even smaller slice than an object, such as one action that can be taken by an object, such as a security check. And you make this in modular form, so it can be duplicated incorporated into any other program. So the trend in general is modularity for reuse. Modularity for reuse in many, many programs without having to recode it. No sense reinventing the wheel so many times. So that's a trend in programming languages. Now, I'd like to have us all go to page 533, please. Page 533. Now, those were the days, my friend. We're so glad they came to an end. But when the first computers came along, there were just a set of light bulbs or vacuum tubes, to be more precise. And the only way to talk to them was in zeros and ones. The only language they understood. So the program, when you turn it on, isn't going to do anything. You need to give it an instruction for it to do something. Now, if you go to the CPU, it has a decoder. It will decode the instruction that you feed into the CPU. Now, I'll draw the CPU a little bit larger to make my point. In the CPU, there are hardwired some number of circuits. And each of the hardwired circuit will perform a different operation. For example, if you want to add two numbers, all you do is branch electronically into this circuit that will add two numbers. If you want to do a logic check, which is higher, a comparative term, is H higher than A, then you branch into the comparative term. So you have these 32 or so circuits that are hardwired into the CPU. Each one will perform a different computer operation. And all the select control unit the CPU does, the control unit, is it analyzes the instruction and it passes control to one of these circuits, And these circuits are expecting to receive data that they need to perform. So the control unit, before it passes control to one of these hardwired operationals, moves the data that's needed into one of its available registers, also in the CPU. And their number of registers gives some strength of the CPU. We used to have around 16. You may have more of them now. So what the control unit does is it fetches the next instruction to execute from memory, it analyzes it, and it passes control to the appropriate pre-wired electronic circuit inside the CTU that will perform that instruction, and it passes the data that that hardwired circuit is expecting to receive into registers. Then the output of this hardwired circuit is placed into another register. And then the control unit, now the output of this hardwired instruction is now available. And then there will be another instruction that says to store this in some memory location. So we've analyzed in over schematic view what the CPU is doing as it executes a computer instruction. But now we have to link that to memory. This is RAM, onboard memory. And we have these memory chips. Now they are connected to the CPU by the bus. And if you want to execute a computer program, the first thing you have to do is make your computer program available to the CPU. Now usually your computer program is being stored out on some hard drive. So if you click on the icon, then you're instructing the operating system to go out to a hard drive, locate the program you want to run, and move it into memory. So your program is now sitting in memory. And what the operating system does is it moves the first instruction of your program from memory into the CPU. Then the operating system says, bye-bye, you're on your own. It used to say bye-bye completely, where it means that you had total control of the computer and you could wreck it. But now the operating system is like a protective mother over you. If you do anything it doesn't want done, it interferes and gives you, and retrieves control from you and aborts your program or something of that sort. This is necessary for the primary reason that there are probably other programs running at the same time in a multiprocessing environment. So not just a matter of you destroying the running of your program, you could destroy the running of other innocent programs. So you are very much watched for what you are allowed to do by the operating system and every instruction that you execute. So what I wanted to analyze in a little bit more detail is, what is it that is sitting in this first instruction position? What is it that is sitting there? Well, the computer only understands two symbols. What are the two symbols that it understands? 0 and 1. So I can predict with confidence that what is sitting there is a string of zeros and ones. Now this is a computer instruction. And it is present in its lowest level form. This lowest level form is called machine language, because it's the language that the machine understands. And in the first days, programmers coded in the only language available, zeros and ones. They wrote their programs in these two symbols. That's all that were available. Now, this is one instruction that I've written on the board. And those of you that are really good at machine language will know that this part of the instruction right here is the opcode. This particular one says add. It's going to fire the add circuit eventually, and the CPU looks for it. This is the operation code for the instruction add. Now, if this program has 32 different operation codes, then it's going to need how many bits for the opcode?
16.
5. 2 to the 5th is 32, agreed? So you see, I actually covered 6, but that's a slightly stronger machine than 64 opcodes. So these opcode, which is the circuit that the CPU is going to fire, is designated as the first part of your instruction, agreed? Now, what is the rest of this out here, these other two pieces? There are two pieces. Well, what I want this instruction to do is to add two numbers. And this is the memory address. Of the two numbers. This is the memory address of the first number. Now, memory has mailboxes on it. The memory has a mailbox, okay? Now, for example, if you have 8 gigabytes of memory in your computer, which is almost a normal computer these days, agreed? Now, remember, 1 byte is 8 bits, true? And 1 byte is the amount of data, amount of storage to hold 1 character in the ASCII system, okay? So that's why we're measuring it in bytes. It's historical, but let's see a little bit more detail about what that memory setup is going to be like. First, if I have 8 gigabytes, then let's say I have 8 memory chips. And each one holds 1 gigabyte of memory. And you saw these chips when you popped the lid on the PC. And those of you that wrote chips on the test lost credit because they should be called memory modules. But we all call them chips, so that was one of your 4 givebacks. So we have these memory modules. And it's divided into, each one of these is divided into 1 million byte locations. 1 billion byte locations, a gigabyte, agreed? 1 billion byte locations. So now, the bottom line is that each one of these locations has a different address than any other location. And those addresses are numbered from 1 to 1 million, 1 billion. So each address is numbered. So if you want to go to this address, you go directly to that address. So this is the memory address that you will go to. And at that memory address, it has been prearranged that there will be a number waiting for you as the first number you want to add. And what the CPU does is it fetches that and it puts it into a register. Now, what would you think that these bits are representing? They're representing the address of the other number that you want to add. So this is its address right here. Now, I wrote the address in binary, and would indeed have many, many more bits than that because of the size of the memory chip that we're talking about. But the principle is that each memory location has a unique address. And the CPU will go directly to that address in one step and fetch what is there. Now let's talk about word size. If this is a 1 billion byte chip, it has 1 billion bytes. Does that mean that I will have 1 billion numbered locations? Not true, because the width of this bus, let's take a modern computer, is 8 bytes, which means it's a 64-bit bus, agreed? How many of you have 64-bit computers? Some do, don't know it, okay? Check your system. Go to the system and control panel. And see if you have 64 bits. You probably do. That means that the width of the bus from this memory to the CPU is 64-bit or 8 bits wide. And that is the smallest amount of transferable memory. When it goes out here and fetches some memory, even though it only needs 1 byte, it is constrained to fetch 8 bytes. It can't take less. So that means that we don't need to label 1 billion computer bytes because it can't fetch 1 byte. So if we divide this into chunks of 8, then we get the number of numbered locations, because a numbered location only changes every 8 bytes, because it's not going to fetch less than 8 bytes. So that's the numbered locations that are in memory. So let's review what is in a machine language instruction. The first element is the operation code, which is the operation that you want the CPU to perform. The next 2 fields, in general, will represent 2 memory locations. Now those won't always be used. For example, after this calculation is done, you will have an instruction that takes the calculation result and puts it back at some memory location that you selected. That would be the store operation. So we fire the store circuit, and then do we need 2 instructions, 2 addresses? No, so one is just left blank. And what would be contained is the one memory location that you want to store the result to. So let's look at this selected page. At the top, we have the operation that I have been describing to you. Now, to make life a little more understandable for you, although not realistic, the writer of the book has put the operation code and the memory addresses in base 10 form, decimal. So the first thing I know you want to do is convert all those numbers to binary, so you really see what the machine code is actually doing, agreed? But let's just pretend that you did that. Then that string of zeros and ones would tell you exactly what this instruction is going to do. And the first part of the instruction is the operation code, which corresponds to one hardwired circuit inside the CPU that will be fired. The next corresponds to the memory address. And the way that this CPU is operating is that this is the, it will move what is at the memory address into a register. And this is the address that the CPU uses for register 0, its first register of the 16 registers. Okay. The next highlighted operation is the decrement operation, in which case it's an operation that is hardwired to reduce the contents at that location by 1. So at this address location, 001004, there will be a value. Say the value is 7, stored at that location. So after the decrement operation code executes, that 7 will have been changed into a what? If you decrement 7, what do you have? 6, all in favor? So the decrement instruction will do just what it says it'll do. Suppose you have an increment instruction, and you have a 7 sitting at that memory location. It'll be upgraded to an 8. Good. Now there's also an end operation code, which is sort of self-explanatory. Now, the first computers that came out, as I might have mentioned earlier, they ran one instruction at a time because we didn't have hard drives. In those days, if you wanted to get some data into the computer, not instructions, but just data, then what was the medium of choice to put your data into the computer? How many of you have heard of a punch card? Okay, well, we had cards that were about the size of one of these ships that I've drawn, and they had, they're made of thin cardboard, and they had a number of columns on them, and each column had 8 rows. So depending on which columns you punched in any given row, you would punch in the ASCII code of a character. Agree? So this punch code was a mechanical way of digitizing data. And it created a vast career field for people called key punch operators, who just transformed the data into punch cards. Punch cards were then placed in very large trays. And for example, base supply inventory had 30 trays of punch cards. Okay? Now the punch cards were read in by a card reader. Now cards don't like to be read, and there was a vacuum to attempt to bring them in easier, which often failed, and you would have what's called a card jam, which you then had to take apart and make the thing run again. But that was just to get the data into the machine. Now you say, well, how does the data get into the machine? Well, you had an opcode also for read the next card. And that fired a circuit that read the next card in the card reading machine and moved the data in that card into pre-assigned memory locations. It was all very crude, it was, I agree. It was certainly a lot faster than the adding machines that they replaced. So it was a big step upwards. But to get the instruction to read the next card into memory, there were 8 toggle switches on the front of the computer. And you toggled in the instruction 8 bits at a time. Then you pressed fire, and it ran that instruction. So this was a very slow and tedious job, granted. So a mathematician named John Newman created the concept of a stored computer program. Instead of entering your computer program one instruction at a time into the CPU by toggle switches, we want you to write all of your instructions down on paper for the entire program. They will be punched into a set of cards. Those cards will be read by the computer before it reads the data. They'll be stacked at the front of the data tray. And each one of those cards will be stored in memory. And then you just transfer control to the first memory location, and everything is automatic after that. So the stored computer program relieved you of using the toggle switches. Unfortunately, the program still had to be written in the only language that the computer understood, which was zeros and ones. So it was a very tedious job. And there was a lot of burnout, as you can imagine. People didn't really last long in that environment. So someone said there has to be a better way, and there was a better way. And someone decided this. They said, I want to create a new language. And this will be a language in which you can write your computer instructions in ordinary English characters, A, M, L, want to multiply two numbers, use M. If you want to add two numbers new, use A. And then, if you want to add two numbers at two memory locations, I'm going to allow you to identify those memory locations with words instead of the numbers that they're really labeled by. So you can label this memory location as tax rate and this memory location as salary. And then I will identify at runtime a certain memory location with your word tax rate and another memory location with your word salary. And instead of the word A that you gave, I will identify the actual operation code. So you are now permitted to write your computer program in symbols that are familiar to you, like letters of the English language and decimal numbers. And then it looks like this box in the middle. Instead of writing the operation code for add, which is 063737, identified at the top of the page, you can now write the word add. And instead of writing the address that you want to add from, you can identify it with the word sum. Unfortunately, if you feed these words into the computer, it's not going to execute them because it only executes zeros and ones, agreed? So the person who thought this up is the person that wrote the last program that was ever written in zeros and ones. And what is it that that last program that was ever written in zeros and ones does? What it does is it reads these instructions that you've typed as input, and it outputs the strings of zeros and ones that the computer understands. So it's known as assembler, because this language is called assembly language. You write your instructions in assembly language, the computer can't understand them. But you run your instructions, your entire set of instructions, through an assembler, which reads them line by line and converts them to the machine language that the machine understands as output. And that's called the object file that's created, because it's a machine language file. And it relieves you of having to do it yourself. But of course, this assembler program has to be written in what language?
Has to be written in the machine.
In machine language, agreed? And it's a very difficult program to write. So these assemblers, as they call, were a major achievement. And since each different type of machine, like a North Star, or like a Mac, or like a a mainstream free PC, or with Radio Shack, they all have different opcodes. They all have different sets of opcodes. So each one of these machines had to have its own assembly language program written, translator. These translators written. Okay? And then they issued their set of assembly language instructions that you, the programmer, could use, and taught you how to use them, and you were now free to write in assembly language, which was a huge improvement. Okay? But unfortunately, each assembly language was machine specific. What ran on a Radio Shack would not run on a North Star, or a Mac, or Altair, or anything like that, because each machine had its own designed specific proprietary CPU and opcodes and addresses. So it was a great improvement with also great limitations. And this was called the second generation language, assembly language. And this is spelled out for you on these two pages, 532 and 533. And life went on like this for about 10 years. And the next guy that had the next great bright idea said that he wanted to write a new programming language that was portable. Now, what would it mean for a new programming language to be portable?
Works within different systems.
Works on any of these machines, agreed? So the first two programming language portable that were written were COBOL and Fortran. Anybody ever hear of either of those? COBOL is a common business-oriented language. It was what we used for business purposes. And Fortran was a formula translation. It was used for scientific programs. Now, each one of these was another step upwards in the movement of what the programmer had to do from low level to closer and closer to the English language. So the programs that were written in COBOL are on page 536. And here you have instructions like accept, which means it's going to get something from the input device. It says compute, result equals. And you don't even have to say a different line for add and subtract. You just say compute and you put in your signs. Now this is far removed from zeros and ones. And unfortunately, it's also far removed from assembly language. So the people who wrote this new portable language then had to write another translating program that would translate these instructions into assembly language. Then those instructions that were translated into assembly language were then run through the assembler and transferred into zeros and ones. So this is the third level language, and it requires two translations. Now, what is the great advantage of this? That if you wrote your program in these COBOL instructions and you were working in an IBM shop, then if you left the IBM shop and went to another shop that was running DEC computers, your COBOL program would compile on the DEC computers. If you left and you went to another company that was running, say, Fuji computers, your COBOL program would compile on the Fuji computers because your programming language in COBOL is portable. It will run on any one of those. Okay? Now, each one of those companies, IBM, Fuji, Sony, then had to have their engineers write a translating program that would translate these universal COBOL instructions into the specific assembly language for their machine. Then they had a specific company proprietary assembler that would translate down to machine code. But that only had to be done once, agreed? So these COBOL programs were portable among all of the different vending machines that were out there. So they were a huge step forward. And Fortran was equally advanced as far as the ease of writing and the fact that your Fortran program was no longer machine specific. You could run it anywhere, as long as the maker of that anywhere had created a Fortran compiler. So these compilers are extremely difficult programs to write. Now, IQ question. If you worked for one of these companies and you wanted to extend the compiler ability to programmers, then you had to write the translating program that would translate those COBOL instructions into the assembly language of your machine. What language do you write this translating program in? Dig deep. Dig deep.
Assembly language?
Hmm?
Assembly language?
Yes, well done. You write it in the assembly language for your machine. You write it in the assembly language for your machine. Good. Now, there's two sides to every coin. There's some good, there's some bad. What are the good points about moving up to a portable language? So Jordan H., name a good point for going up to a portable language.
You can use it on different types of systems.
Use it in different types of systems. Another good point, George G.
It's not stuck for just one system.
Boom.
Got it.
Gotcha.
Say finished.
Finished.
It's pretty good.
Sierra, which of these two would you rate as the better
The better Jordan?
advantage? Yeah, which
Oh.
is the superior advantage?
Oh. That's really what I thought you were
More important, which would be
I'm
more
saying.
important? The fact that it runs on different systems, or it can be run on more than one system?
That's a hard choice.
Yeah.
I don't know.
Okay, now let's look at productivity costs. In the early days, machines were very expensive. And the running of those machines was also expensive, because you're running out the capital, agree? And programmers were cheap. So it didn't matter if they worked 1,000 hours on machine code, so what, they're expendable. But as time went by, the cost of machinery hardware came down, down, down. And the labor costs of programmers went up, up, up. So now, can you compare the labor cost investment of a programmer writing in COBOL and a labor cost investment of a programmer writing in machine language? Takes a lot less time, saves you programming labor expenses. That's what Georgie was trying to say. He was getting there. Okay, so you bring down programmer costs very greatly, agree?
More accurate too.
Yeah, it's more error-free, and that's all true, and has self-checking internal
Ones and
steps.
arrows, you got words.
That's right. Now, what about documentation? Your zeros and ones, when you leave the company, your replacement has to understand your program, so you just give them the papers of zeros and ones. No, so you write some English language documentation on side pages, agreed? Which doesn't help all that much. But this COBOL code is advertised to be self-documenting. In other words, as you read the code, the words, you know exactly what the program is doing. It's computing the result plus the number, whatever that is. That's not a good number. Label. You're free to name these labels anything you want. And one of the things that you want to do is choose words that make your line of code self-documenting. So a new person knows exactly what that line of code. You say, add current, multiply current tax rate by employee's latest weekly salary. You can use those for your memory labels. And it tells exactly what the line of code is doing. So they're self-documenting, another huge advantage. Now, what's the big, big disadvantage of these high-level languages? It's this. One of these beautiful words, like compute, result equals result plus sum, has to be translated into some assembly languages, agreed? Turns out if you translate that into assembly language, it takes about 8 assembly language instructions to get it done. And then that has to be translated in machine code. So you're going to end up with about 20 instructions to actually perform this one. Whereas if you wrote it directly in machine code, you could do it in 2 or 3. So it's highly, highly inefficient. When you go through the translating process, get it done in machine code, it produces large, large object files, much larger than would be produced if you wrote it with machine language, which is very hard to use but highly inefficient. Assembly language is also very efficient. One operation, one line of code. Another operation, another line of code. In a language like COBOL or Fortran, you have one line of code is going to generate maybe 10 or 20 assembly language lines of code, which is highly inefficient. So that means that you have large run times on your machines, agreed? And that means your programs produce results slowly. Now, that's not acceptable, especially on high-end scientific processors that are going to do 100 million iterations to do a numerical integration, for example. Speed is important. On business applications, it's not so bad because you don't do that many computations. But on business processes, you often have large numbers of data. For example, if Bank of America is calculating the current balances of all of its customers, It's a very simple calculation for 10 billion customers, agreed? So, execution time, one way or another, matters. Now, which has the better execution times? The program written in a high-level language, like COBOL or Fortran, or the same program written in a low-level language like assembly? Low-level has higher execution times. So it's a trade-off. So some programs, even today, are still written in assembly language where that execution time is precious and is needed. So now the stage is set. The year is around 1960, 1980, in that era right there. We go to Bell Labs, a major research lab. We go to a man named Dennis Ritchie, and he says, I'm going to write a new programming language that is going to be high level, so it is as easy to use as COBOL or Fortran. But I'm going to write it in such a clever way that it executes just as fast as assembly code does. And he did it. And what did he name his new language? C. It's still probably the most respected and revered programming language we have because it does exactly what he said it would do. It's very readable, it's easy to code, you can learn how to do it quickly, it's self-documenting, but because of the clever ways in which he wrote it, it executes at assembly language speeds. So it's used still very, very strongly for scientific applications because of its speed of execution. It's used somewhat for business applications because it's not as self-documenting or as obvious as some of the others. But by and large, you can say that C was successful, at least for a while, in replacing both COBOL and Fortran. Then Fortran developers made their Fortran even faster, so it's gained the edge again in scientific applications. Point.
The text said that there was three C's, C, C++, and C pound.
Yeah.
Are those just updated?
C sharp, sir.
Oh, C sharp. Is that just updated C?
Yes,
So,
right,
C pound.
right. How many people in here know the least little thing about music? The pound sign is pronounced
Sharp.
Thank you.
Little bit flat.
I like C pound.
Okay, now, let me share with you
Yeah, I
why,
was gonna say, I was gonna say hashtag, you're good.
let me share with you why the C, which was the original, was next called C++. The next improvement of it. Now, the improvement from C to C++ is that you went from a procedural language to one that used objects. But the actual instructions themselves were not changed. It just had a new add-on that you could use objects besides just straight instructions. But it still uses the same C code. Now, in the C programming language,